talk about domain wall superconductivity. Czy trzeba przykładać?
Nie ma, już jest.
To już trzeba przełożyć.
Professor Ritta Szymczak was also involved in different type of experiments, namely about the competition between ferromagnetism and superconductivity. This was on this topic. This group, with cooperation with Professor Moszalko from Leuven University, they published 4 papers about this topic. And the group in Leuven was known from the study of such ferromagnet superconductor system for study of magnetic field mechanics. However, before I start to stress this results of the experiments on ferromagnet superconductor structure, I would like to shed a light on, first of all, on the existence of 2 antagonistic phases, namely ferromagnetism and superconductivity. Then I would stress quickly about the proximity effect in ferromagnet superconductor system. I will just mention only how many different kind of phenomena can occur at such system composed of ferromagnet and superconductor, and then the main topic, namely the superconductivity related with in ferromagnet superconductor between superconducting and normal metal. Then in normal metal we have non-zero vector potential, pile potential in normal metal, and this effect is long range. It can occur up to 1 micron or even more. And quite different story is if we have ferromagnet in contact with the superconductor. First of all, of course, if the exchange field is very large, I mean, generally Curie temperature is much larger than the critical temperature, then superconducting state will be suppressed. And this is so-called, as I mentioned earlier, paramagnetic limit. So this means that the exchange field is breaking copper pair. However, if you will have a moderate ferromagnet, then due to Zeeman effect, there will be splitting of levels, and in such case, Fulde, Ferrel, and Larkin of Chinkov show that in such case there is not the other parameter is not monotonically decreased, but it's oscillating, damping oscillating, and such phenomena is very short range, up to 1 nanometer. And in such case, the momentum is non-zero. I mean, why I'm talking, because if we have, I mean, because there are very few ferromagnet superconductor systems. As I mentioned, holmium molysulfide, erbium, rhodium borates, uranium, germanium-2, and there are very few. However, because due to progress in film deposition, we can make different kind of structures. And very nice, for example, a very interesting case is so-called p-type junction. Namely, before that, there was many experiments going on where two superconductors were separated by ferromagnet. And as the thickness of the ferromagnet has increased, the TC do not decrease monotonically, but TC showed minimum and then again increase. And the explanation for that is so-called is just Hurdeferel-Larkin of Chirikov state. It means that we have non-zero momentum, and in such case, if the real part of the parameter can be negative, and if it's negative, then we have so-called pi state. And density of state for zero junction looks like that, whereas just quite opposite for pi junction. This was demonstrated experimentally by Cantos, where, of course, they used diluted nickel palladium as a ferromagnet, and as we see, we observe this type of behavior. And because of this relation, this should be phi plus pi, that's why it's called pi junction. I mean, and there are, of course, many more different kind of phenomena occurring at ferromagnet superconductor. There is, for example, can occur if we have ferromagnet, a superconductor ferromagnet superconductor structure with non-homogeneous ferromagnet, we can induce triplet state. These are phenomena related with proximity effect. In this case, Professor Ritta Szymczak was, as I mentioned earlier, with Professor Morshalkov group, studied how the interaction between two competitive states between ferromagnet and superconductor. And as my colleague presented earlier, I didn't know, Professor Ritta Szymczak published this paper about the magnetic properties of the system, which I will show later, much earlier. That's why she knows the domain structure, which is important here. I will just show the result because they are similar from two papers. One published in Nature Materials. This is local observation of reverse domain superconductivity in superconductor ferromagnet hybrids and domain wall superconductivity in superconductor ferromagnet, where they present the visualization of this state. But before I go to presentation, I will mention just about the paper by Aladishkin, where they theoretically considered such system composed from superconductor and ferromagnet. They take into account ferromagnet, which has easy axis perpendicular to the surface, and to do this, they use Ginzburg-Landau model. It means close to TC. They linearize this Ginzburg-Landau equation and transform them in such equation, which it reminds the Schrödinger equation. And they study how non-uniform magnetic field, the impact of non-uniform magnetic field on other parameters. And for example, here there are results. If we have one block wall, then there is show the localization of the other parameter. And here, of course, they consider different kind of systems with different type of magnetic modulation. Here we have periodic modulation of domain walls, and the position of the other parameter, which goes like curve. I mean, generally, the experiment, we have such conditions that the perpendicular component of apercritical field is much lower than the parallel. So the impact of this perpendicular component is generally important. So the first paper, so as I said before, Professor Ritta Szymczak published already domain structure about this system. And presumably, they also conclude that this system is very useful to study this kind of behavior because, first of all, saturation is very low. The upper critical field is much higher, so it means in zero magnetic field there are optimal conditions to study this effect. However, how they do this? First, the single crystal with the thickness about 90 microns was cut. Then, in order to avoid the proximity effect, as I mentioned earlier, they deposit 10 nanometers of siliconium and then 60 nanometers of niobium. Generally, the domain wall width is very large, about 2 microns, whereas in Aladeshkin model, they assume that the domain walls is 0. So the idea of the paper was to observe superconductivity in such heterostructure. And the idea is following. If we have applied magnetic field, the first maybe, let's consider the first case where the external magnetic field is 0. I mean, generally, if according to Aladeshkin model, the position of the other parameter will be situated where the compensation effect is the largest. It means here in the case is located at the Bloch wall. If we applied magnetic field, for example, in the opposite direction, then superconductivity of this area will extend from domain walls up to domain part which have opposite magnetic moment. So this is the idea of the experiment. And here you see, first of all, the magnetic properties of this single crystal barium, iron, oxygen. And as we see, this is almost reversible. So it means that domain walls are moving. Only small irreversibility is seen close to the saturation. Here is extended. And these measurements were done in 5 Kelvin and in room temperature. And the magnetic domain structure was studied using magnetic force microscope at room temperature. But because the magnetization curve at 5 Kelvin and at 300 Kelvin are similar, that's why they assume that the structure. So we see in zero field branch-like system where this yellow is the domains with magnetic moment according to the applied magnetic field, and the opposite are red. Now, if the magnetic field is increasing, we have more so to say yellow areas. It means that the positive domains more, whereas at higher field and in some cases the opposite domains have shape like stripes. And then again the evolution at some magnetic fields close to the saturation we have bubbles, and then around 3.4 there is saturation. of the magnetization. And now, decreasing magnetic field from saturation to zero is similar. Now, let's have a look on the transport measurements. In this figure, we see two types of curves. In this inset, we see, because the niobium film deposited on this single crystal and on silicon. So on silicon, the resistive transition behaves as one can expect. It means the larger magnetic field, and Tc is shifted to lower temperature. And non-monotonic behavior is seen on this heterostructure. First of all, in zero magnetic field, so we see some transition. Now, if we increase magnetic field, the curve is also similar. However, if we applied some magnetic field, namely close to saturation, saturation is around 5.4 kilohertz. We see that Tc is higher than Tc in zero magnetic field. They assume, because of course, according to Aladashkin model, it's not easy to compare. First of all, the domain wall width is 2 microns, not zero dimensional. So nevertheless, they apply so-called isolated domain model, and they could describe the phase diagrams, which was they could, from this experiment, they could find all these parameters, and as you see here, so this is the range where the superconductivity exists on H2T diagram, and this is for three criterion for if the resistance will decrease 10%, 50%, and 90%. Now, how to understand this behavior? First of all, I mean, if we increase, here we see the dependence of resistance versus magnetic field. If we go from plus 10 kilohertz and then we will decrease the field, then we have some minimum. This is very close to Tc. And then, if we on opposite side, a strong dip of the resistance. And then if we lower the temperature, more or less the situation is the same. However, the dip are almost comparable. And how to explain this fact that Tc in magnetic field is higher than in zero magnetic field? In such case, if we have superconductivity, because the compensation effect in zero field is largest at domain walls, then if we apply magnetic field, then the compensation effect is the largest where we have reverse domain. So it means that the nucleation superconductivity will occur not only at the domain walls, but also on the area underneath. That's why this fact this fact in fish of Tc demonstrate the inducing superconductivity in reverse domain walls. If we decrease the temperature, then superconducting state, this effect will disappear. The reverse domain will stay only at the domain wall. So this is, I mean, and here you see the change of the resistance, because I mean, generally, not only the compensation effect is important, but also the number of, or the area of reversed domain wall, the reversed domain. And there is a strong correlation. And that's why this resistive transition strongly depends on the history of the measurements. The other, the next paper, the idea of the next paper was to demonstrate, first of all, domain wall superconductivity, reversed domain wall superconductivity, and if you will go with critical temperature much lower, then of course, if the external field is lower than upper critical field, then we have so-called parallel domain structure. It means that the whole area is superconducting. And again, this is the magnetic domain structure of the single crystal made by magnetic force microscope. This branched type, the yellow, represent positive and the brown negative. So if the magnetic field is increasing, this branched structure disappears, or the area of reversed domain area becomes smaller, and then close to saturation, which is around 260, if I remember, then we have only the bubble. And similar situation as previously, the magnetization curve that was made at 5 Kelvin and at room temperature. So they are very similar. That's why the authors assume that the domain structure at 5 Kelvin is very similar to that. At 5 Kelvin is similar to that at room temperature. And this experiment was done they did a bridge. The bridge had around 40 micron width and 130 micron width. And they used so-called laser scanning laser microscope. It means what they did is they illuminate the bridge with the laser. It means they heated the bridge. And nevertheless, the area underneath have different TC. And they measure resistance in situ using lock-in technique. And here you see the results of such measurements. At this picture, the area described by B, if the temperature is increasing, is growing. There is a lot of this area B. This is at 200, because they, as you see, they did measurements at 2 magnetic fields. Whereas, and that's why, if we measure the bridge, and so we have kind of percolation part. So if this B extends from one end to the other, then we see superconductivity. Then the different story is if we have higher magnetic fields. We observe the areas described by A. And if the temperature is growing, the A is disappearing, but B is appearing. So you see here the derivative of resistance by the temperature along such taken at such measurements. So now the composed picture, because at lower magnetic field dominates the area described by B. That's why this area B is, so to say, reflect to reversed domain, whereas the area described by A describe the parallel domain structure. It means that we have superconducting whole system from the above. So to conclude, the authors observed so-called domain wall superconductivity, especially in this barium iron oxygen system. They observed reverse domain structure, and then they visualize this using this scanning laser microscope. They visualize reverse domain structure and parallel domain structure. Thank you very much.
Dziękuję. Jakieś some short questions?
I just wanted to add one comment. Maybe Piotr didn't know about it, but myself and my collaborators from Johns Hopkins University and my graduate student, we have worked also on this same problem during last several years. We have published several papers on this in somewhat different structure, but essentially the idea is the same, that this is the effect of orbital interaction between the magnetic layer and superconducting layer. And so it's not that this idea has died, it is followed at our institute, so we're also followers of Ritta.
Thank you for this comment.
It's interesting that these domain walls are really very strange system. For example, it was shown just recently that in garnets, rare earth garnets, in domain walls, ferroelectricity may be used. Not only superconductivity, but also ferroelectricity. So the system is extremely rich.
To zapraszam na 15 minut przerwy. Za 15.
This is colossal magnetic field. More. This homomolet layers cobaltite, first of all, associated to this configuration with Pani Ritta, because the majority measurements were carried out here. We show that this compound exhibits very large magnetic resistance and magnetic fields with homovalent state. We show that the ground magnetic state may be or antiferromagnetic or non-collinear ferromagnetic. The transition between non-collinear and collinear antiferromagnetic lead to jump of conductivity and associated with large magnetic resistance, because external magnetic field shift this transition to lower temperature. It was published at first in
physical regulators. This slide is symbol because this history compilation. This compound, homovalent manganite with perovskite structure, also exhibit transition from orbital to disordered orbital structure. This phase transition is associated with jump of magnetic susceptibility, but in disordered state, this compound is ferromagnetic. The lanthanum, manganese, O3 doped by gallium also exhibit ferromagnetism, but insulated ferromagnetism, with Curie point about 70 degrees. So homovalent compounds exhibit ferromagnetism in spite of absence of mixed valence. We show that the homovalent stibium or niobium doped compound, homovalent manganese, also ferromagnets, and exhibit ferromagnetism up to 150 degrees Kelvin. However, mixed valence manganese doped by niobium and magnesium, 5 valence niobium, 2 valence magnesium introduce charge carriers, magnesium's 4 valence. However, unexpectedly, magnetization decrease with anti-magnesium doping, 4 valent doping, decrease. Magnetic structure and crystal structure, this compound, does not change under doping, but Curie magnetization and becomes below. There is another mixed valence systems, manganese and titanium and aluminum. Only titanium give only homovalent materials. Aluminum introduce manganese 4 valence doping. And unexpectedly, the homovalent compound exhibits the most pronounced magnetic resistance. Unexpectedly. All these compounds does not exhibit tundelic resistance, magnetic resistance. This compound is associated with my philosophical doctoral dissertation. Екатеринбурg, Самохвалов proposed this thematic because he weighed that the ferromagnetism in this compound rise from double exchange. However, we show that ferromagnetism in this compound arises from antiferromagnetic exchange between cuprum and manganese. Exchange interaction between manganese are close to zero. But that these compounds exhibit strong spin polarized electrotransport. The optimally doped compound, calcium manganese, is spiral antiferromagnet. Yes, this transition and this compound was first synthesized by our group. this is resistance and magnetic resistance in bismuth cuprum 10412 compound. This compound also was have been synthesized at first in our group. Exhibit transition at Curie point, at nail point, and similar magnetic resistance to magnetic resistance as manganites, standard manganites. Ferromagnetism, ferromagnetism, but fact picture is similar. Mixes valence cobaltite doped by iron ions. Under iron doping, magnetization gradually disappears. There is a peak of magnetization in heavily doped compounds. But standard cobaltites are metallic both in magnetically ordered state and paramagnetic state, and does not exhibit large magnetic resistance. However, magnetic resistance in iron doped cobaltites very large. Very large. And observed at low temperature. First of all, we show that the antiferromagnetic phase and ferromagnetic phase in this compound phase separated, but using the Newton diffraction method. And antiferromagnetic has much larger volume unit cell than ferromagnetic. So we propose that the antiferromagnetic in different spin states concerning ferromagnetic compound. Ferromagnetic intermediate spin state, antiferromagnetic high spin state. High spin state has another electronic configuration than intermediate spin state. So jump electroconductivity under field, external field is associated with spin transition from high spin state to intermediate spin state. Conclusions. I think that the super exchange model is very good alternative double exchange model. And many magnetic resistance effects, ferromagnetic ordering effects very well can be explained in super exchange model. I have some discussion with John Goodenough. We have common conclusion that the super exchange interaction very important for mixed valence manganite, because in mixed valence manganites there is very low density of charge carrier at Fermi level. The majority of EG electrons are localized. This localized electrons transforms structure, magnetic structure into ferromagnetic through via super exchange, Anderson exchange. I note that the model Zinner was very close to Goodenough because of history. My recent publication. Thank you for attention.
Dziękujemy. Czy macie Państwo jakieś pytania, komentarze? Profesor?
Do you observe superparamagnetic state on your SEMS?
Superparamagnetic state is typical for this compound, but is no narrow range between ferromagnetism and antiferromagnetism. Superparamagnetic state is not critical for magnetic resistance. For magnetic resistance is critical band structure. Unical band structure is compound. Because external field may can shift some
if
bands.
you see superparamagnetic state, you have some aggregates or clusters magnetic on this sense. How these clusters influence on this
Cluster
property?
spin. So note the grand state. Grand state in this compound or unique phase state, unique, or two-phase state. Intermediate state, superparamagnetic state.
Some other comments, questions? If not, thank you again. And the last presentation will be given by Professor Piotr Pawlik from University of Technology in Częstochowa. Please.
Thank you. Ladies and gentlemen, this is my second time I have this opportunity to present my talk at this respectable institution. First of that was my PhD presentation, where I was shaking in front of Professor Ritta Szymczak, Professor Henryk Szymczak, and giving a talk. And then, I remember that after my talk, Professor Ritta Szymczak at a little party was giving advices to my wife how to live with the scientist. I think that she took these advices, I hope, my talk will be slightly, at least touch some subject of interest of Professor Ritta Szymczak. She was interested in various areas of magnetism, and I'd like to talk about things that we are doing in Częstochowa. I will talk about the rapid solidification techniques that we have developed in our institute and materials that we have produced using these techniques. And I'll talk about the magnetocaloric materials. This subject was of the interest of Professor Ritta Szymczak very much. And I'll talk, if the time will be, I'll talk about co-precipitation of nanoparticles for hyperthermia studies. This is the subject we are just starting, so this is the new subject of study. Yes. Sorry. Rapid solidification, in order to get fully amorphous structure, one has to avoid the nose of this trying temperature transformate curve with the cooling rate high enough. When the cooling rate is not that high and touch the nose of this curve, we end up with a nanocrystalline structure. When it is very low cooling rate, it will result in crystallization in microstructure. So on the other hand, when talking about the alloys, the critical cooling rate for a particular alloy have to be low enough in order to get a large section of the amorphous materials. There is a quite large number of bulk metallic glasses up to now, which were processed. Not very significant. The other alloy, we have moved to some alloys with higher amount of rare earth, 9% atomic percent, and we were able to cast directly nanocrystalline structure in a form of rods and tubes, and also for the very thick ribbons it was possible to cast partly crystalline material, nanocrystalline material, which reveals quite high coercivities, roughly about more than 1,000 kiloamps per meter for the thick ribbons and tube samples, while for the rod samples it was a rather moderate coercivity. The other subject, which was also in the interest of Professor Ritta Szymczak, was, and also we are studying this sort of things, is a magnetocaloric effect at room temperature. The magnetocaloric effect might be assessed by the measurements of the direct measurements of the change of the temperature with the change of external magnetic field, or by the change of the magnetic entropy with the change of external magnetic field. For those who work in magnetic laboratories, the second possibility is much easier to gain, and we have just done such a measurements. We have chosen for our studies this lanthanum iron silicon 13 type phase, and the alloys based on this phase, because it is cheaper than alloys containing gadolinium or pure gadolinium, and also it is easier to tune the Curie temperature for this material by appropriate doping. One example of our work is the lanthanum iron cobalt silicon alloys with various cobalt contents, which show that with the increase of cobalt contents, the change of the unit cell parameter for this lanthanum iron silicon 13 phase occurs, and also magnetic properties shown by the Mesbauer spectra analysis, and also by the magnetization of these temperature measurements shown such a change. We have done a mixture of those all compositions by crushing to powder, ball milling, and compacting into the pellets, and measured something like the Mesbauer spectra, X-ray diffraction, and also some magnetic measurements. And we have shown that the magnetic entropy change takes a table-like shape with the temperature. One have to remember that for the room temperature applications, the magnetocaloric materials have to work in a range of temperature, not in a single temperature, but in a range of temperature. Therefore, it's just an example how it is possible to gain that. The last part of my talk will be concentrated around something that we have just started. This is the co-precipitation of iron oxide nanoparticles for hyperthermia studies. Hyperthermia is a cancer treatment that involves the heating of the human tissue in order to kill the cancer cells, because the cancer cells actually deteriorates at the temperature roughly about 45 degrees centigrade. The problem is the reason for that is that the thermal conductivity of the cancer cells is lower than in case of healthy cells, so that the healthy cells will easily dissipate an energy, but while the cancer cell will accumulate the heat, and they will can be that way damaged. So one of the methods which is at the moment very popular is to use magnetic nanoparticles in a fight with a cancer, and for that is used some iron oxide nanoparticles, because those particles are actually allowed in the medical community to introduce to the human system. So we have done co-precipitation of these nanoparticles from salts, this type of salts, in the ratio 2:1. There are sources of iron-3 and iron-2 ions to this solution of those salts. We dropwise added ammonia hydroxide, and the process was carried out in nitrogen atmosphere at the temperature 60 degrees centigrade. For the part of the nanoparticles that we have collected from this process, we have done the Stauber process, which is the process to coat this nanoparticle with silicon oxide. For this purpose, we have used tails, ammonia hydroxide, and 2-propanol, and ionized water, and ultrasonificated that for 6 hours at 60 degrees centigrade. And we have done X-ray diffraction for those these nanoparticles, which shown that the nanoparticle, that actually Rietveld analysis has shown that the nanoparticles had the size of the order of 15 nanometers, and this is a single-phase structure containing only magnetite nanoparticles. For the coated nanoparticles, we have seen the same diffraction peaks. However, and there was a lack of peaks coming from the coating, so that we assume that the silicon oxide forms a coating as an amorphous coating around the nanoparticles. Bauer spectral analysis shown presence for the coated nanoparticle additional component of the convolution, which was a singlet line, not seen for the non-coated sample, which is, we assume it has to be actually confirmed. There are two possible explanations for that. One of that is that the nanoparticles are separated by this coating, and this results in a transition to sort of superparamagnetic state. But I'm not convinced about that. I rather would assume that the iron atoms on the surface of nanoparticle will interact with the surroundings coming or silicon oxide surroundings, and thus this affect the shape of the Bauer spectrum. We have constructed homemade the equipment for measurements of the time dependence of the temperature, which is the alternating field generator connected to which is connected the induction coil. Inside of this induction coil, there is a thermally isolated container where the sample is introduced, and the temperatures versus time is measured. And we have done actually just these are just recent measurements. We have done measurements for two different alternating external magnetic field, 2.4 kiloamps per meter and 2 kiloamps per meter. In case of 2 kiloamps per meter, the frequency was, in both cases, was 100 kilohertz. In case of 2 kiloamps per meter, we haven't succeeded in heating those nanoparticles. However, in case of the 2.4 kiloamps per meter, we have reached this temperature 45 degrees of centigrade after about 60 seconds. The studies of this effect are still going on, so I'm sorry that I just presenting only a few our results. I had no clue how to conclude this talk. I just take this opportunity to just present that we are open for the collaboration with this respectable institution. Thank you very much.
Are there any comments, questions?
Try to optimize frequency for this.
Yeah, this is as I said, this is our homemade unit. We have to actually do some additional work in order to get different frequencies. This is what is just under construction, still under construction, and I hope in the future we will be able to do some different frequencies as well.
Dziękujemy.
Thank you very much.
Na tym kończy się taka, powiedziałbym, przewidywalna część tego sympozjum, natomiast jeżeli ktoś z Państwa chciałby coś dodać, czy na pewno nie wszystkie aspekty działalności naukowej pani profesor Szymczak udało nam się uchwycić w tych wykładach, chociaż nie wątpię, że każdemu na tym zależało, to jeżeli ktoś chce mieć jakiś dodatkowy komentarz, proszę.
Że po polsku można mówić, tak?
Tak, już teraz.
Z tych 370 prac pani profesor Rity, to myśmy współpracowali z około 4%. I oczywiście dodatkowo to było całkiem inne, powiedzmy, podejście, bo były badane własności magnetyczne, kiedy przy małych koncentracjach nanocząstek magnetycznych rzędu 0,1-0,3% wagowego, no i badaliśmy te właściwości magnetyczne, które były bardzo interesujące. I drugi kierunek to były bananady. Są to związki właśnie dosyć skomplikowane, magnetyczne i oczywiście one są, unikają większość środki, bo się okazuje, że tam ze względu na banat są dosyć niestabilne te własności fizyczne zastosowania. Ale z punktu widzenia fizycznego są bardzo ciekawe, bo tam występują i efekty kompensacyjne, efekty właśnie frustracyjne, przejścia fazowe itd., itd. A zaczęło się wszystko od projektu Tempusa, gdzie po prostu...
Pierwsza praca wyszła w archiwum elektrotechniki. Ale ciekawe to, że w tej pracy, o której mówię, w tej książce, w tej Biblii ludzi, którzy się zajmują domenami, to Hubert zapoznał się z tą pracą, bo prawie jedna strona jest temu poświęcona. Chodzi o zależność struktury domenowej od grubości warstwy, a ta praca była nawet po polsku napisana. Więc, ale cytowane jest rzeczywiście mało, jest tylko 8 cytowań. Ale gdyby to było opublikowane w normalnym czasopiśmie, tak jak teraz publikujemy, to myślę, że sytuacja i w przypadku profesora Troyanchuka, i w przypadku Ryty byłaby lepsza. No ale najważniejsze, że te rzeczy nie zginęły.
Proszę.
Ja wiem, że tematem naszego spotkania są omówienie osiągnięć naukowych pani profesor, ale chciałem zwrócić uwagę na jeszcze jeden aspekt. Jako osoba w latach 80. wchodząca do, nazwijmy to szumnie, pracy naukowej, wydaje mi się, że tutaj mogłem mówić o pewnej relacji między mną a panią profesor, jako relacja mistrz i uczeń. I wydaje mi się, że też to, o czym wspominał profesor Maziewski w swoim wykładzie o następcach, jacy pozostali, czy to w jego zespole, tak wydaje mi się, że możemy mówić trochę może, tak to zabrzmi zbyt nieskromnie, że tych następców pani profesor także ma w Częstochowie i za takiego także się uważam i chciałem jakby wspomnieć także poza oczywiście tymi naukowymi osiągnięciami, ale tą w tych latach 80., kiedy właśnie te kontakty miałem pierwsze z panią profesor, to odczuwałem tą pewną opiekę, ciepło, bezpośredniość i także na to chciałem zwrócić uwagę, nie tylko na ten aspekt jakby czysto naukowy, także, ale przywołać ten czysto tak powiem, ludzki aspekt. Dziękuję bardzo.
Jeszcze przy okazji, jeżeli pan profesor zabrał głos, to pokażę w tej chwili, to jest wydana w tym roku książka Wybrane zagadnienia z historii magnetyzmu. Magnetyzm w Polsce, hipoteza domen magnetycznych, magnesy ze stali. Tą książkę dostał pan profesor, ale myślę, że ją warto też zamówić, kilka egzemplarzy do naszej biblioteki, także szczególnie państwu, którzy w tej chwili wchodzicie w tematykę magnetyzmu, to myślę, że to będzie pożyteczna lektura. To profesor Wysocki jest autorem. Dziękuję państwu wszystkim za udział. No, myślę, że każdy z nas, nawet jeżeli głośno tego nie mówił, ma jakieś osobiste wspomnienia związane z panią profesor Szymczak. I no, trochę może tak jeszcze raz odwołam się do tego, jak kończyłem swoje wystąpienie, że naprawdę pani profesor Szymczak zaznaczyła swoje miejsce na badaniach naukowych w bardzo wielu takich ważnych momentach historii tego, co działo się w magnetyzmie. I jestem absolutnie przekonany do tego, że warto sięgać do jej prac, szczególnie osoby młodsze, bo szereg z tych prac jest takich bardzo kompletnych, zarówno od strony metodologicznej, analizy wyników, dyskusji wyników, także naprawdę myślę, że prace pani profesor Ryty Szymczak będą bardzo długo jeszcze pracami, do których warto zaglądać i myślę, że tak podsumujemy to sympozjum. Dziękuję bardzo.